All right, hello everyone. So this is going to be a short video. I wanted to just recap the mole ratio and go over a little bit of details in terms of how you figure out the ratio and just kind of touch base on things that we've looked at already. And so here it is. So this is just a short presentation again. So first of all, what is a mole ratio? So a mole ratio is a ratio that's determined by using the coefficients from the balanced equation. It's a ratio that we use primarily to convert between one molecule and another in a balanced chemical equation. Now, the whole purpose of a mole ratio is to be able to calculate things that you might be produced, how much you might need to react. And so this is an application of what we call stoichiometry. And stoichiometry is just a method that we use to convert between differing substances in a balanced equation, hence the mole ratio. So the mole ratio is a very, very key equation. Now, just a couple roadmaps that we've looked at in previous videos. There are grams per mole, and then moles converting back into grams. All right, so if you want to go from grams to moles, you divide by the molar mass, and then the opposite is for going from moles converting back into grams. Remember that all this is based around the periodic table and then paying attention to the molar masses for each of those elements. Okay, so again, for now, simplicity reason, we are going to just add a new roadmap in here, and we're going to call this moles of A converting into moles of B, and we're going to utilize the mole ratio, which is represented by Mr. All right, so the first thing we need to do is to balance the equation, and we're going to look at this example here. Now, it's already written out several steps, but let's just go ahead and get through this. So first of all, sodium carbonate reacts with HCl. So this is an acid, and this is a base. When the acid reacts with the base, it's going to produce the salt plus its other counterpart. And so in this case, it's hydrogen carbonate. Now, in this reaction, you are going to see that you have two sodiums on the left, but on the right, you only have one because the formula is NaCl. So you're going to put a 2 in front of that, and that gives you 2 Nas, and it also gives you 2 Cls. Now, you look at the left side, we need to make sure the Cls are balanced. They are not, so we put a 2 in front. And in doing that, we end up we actually balance the equation. So don't forget that that in front of these, you need to make sure you put a 1. And is it necessary? No, it's not necessary, but it is in our case. So make sure that you know it, because again, we are going to be using the coefficients to figure out what the mole ratios are, and we want to be able to see these coefficients pretty easily, so we don't miss a detail. All right, and that detail would be the 1. So the next step is to just write out some mole ratios. Now, these ratios are going to be dependent on the question that is being asked, but also in this particular case, there's not a specific, so we're just going to be very generic in the answers that we put here. So the first one is just looking at the two reactants. So you have 1 mole of sodium carbonate for every 2 moles of HCl. So it's a 1-to-2 ratio. So if you start with 1 mole of sodium carbonate, you have to have 2 moles of HCl to react with that substance. And then you also can reverse it. In reversing it, you have 2 moles of HCl for every 1 mole of sodium carbonate. You say, why would you reverse it? It depends on the question that's being asked. And then on the right side, we see that you have 2 moles of HCl to 2 moles of HCl. So now this is comparing the reactant to the product, and then it's comparing the product to the reactant. So you can see that there's similarities, but you don't have to always stick between the reactants. You could compare the products, you compare the products to react, and there's a whole different number of possibilities for mole ratios. But again, it goes back to the very basic thing of knowing what the question's asking for and how you answer that question. So that's where that ratio comes into play. So So again, this is just a repetition of what we see up here. So now let's look at a new reaction. So this new reaction is hydrogen gas reacting with oxygen gas to produce H2O. All right, so if we look at hydrogen to oxygen, so of course we want the mole ratio. So we're going to look at the coefficients here. All right, so in the first one, it's 2 moles of hydrogen for every 1 mole of oxygen. So that's the ratio for the first pairing. And then looking at the second pairing here, you have hydrogen to water. So again, you have 2 moles of hydrogen for every 2 moles of water. So it's a 2 to 2 ratio. So again, in this example, we would be looking for hydrogen to compare with oxygen, and this one you're looking at hydrogen compared to water. So you see how the difference between you can compare the reactants and then the reactants to the products. All right, so let's look at a couple more here. All right, so oxygen to water. So what would oxygen to water be? Right, it's 1 mole of oxygen to 2 moles of water. And then if we look at the next one, it's so same thing, right? Yeah, so it's oxygen to water again. So it's a 1 to 2 ratio. Again, this goes back to just utilizing the coefficients and making sure that you put them in the correct placement. And that, again, it depends on the question that's being asked. So it's 2 to 1 for that one. All right, so again, we're going to use the mole ratio to convert between varying parts of a balanced equation. In the end, it is a conversion factor, so that's where that moles of A convert to moles of B roadmap comes into play, and then we leave it a very generic mole ratio. We don't put multiply, we don't put dividing, because it really depends on the question that's being asked. Okay, so looking at the first example here, so at 20 moles of oxygen gas reacts, how many moles of water will be produced? So in this question, we're utilizing that ratio of oxygen to water. All right, so we know that we have 2 moles of water for every 1 mole of oxygen. That's based off the ratio. We see that up here. All right, and so now we are looking for water. So when we plug this in, we want to make sure that the part that we're looking for is on top. So you wouldn't necessarily put the oxygen on top, because that's not the part that you're solving for. You're looking for water. So we're going to put the water on top, and the oxygen goes at the bottom. So as you go through the math and the calculations, you take the 20 moles and you multiply it by 2 and you divide it by 1. Now, when you divide it by 1, the moles of oxygen are going to cancel out. So 20 times 2 gives me 40 moles of water. Okay, so that's a very simple example where we utilize the ratio, and we are applying this roadmap that we see up here, this brand new roadmap. Okay, so now let's look at another one here. So in this next example here, it says if 0.76 moles of hydrogen gas reacts, how many moles of oxygen gas will be needed? Now, so you're starting with moles and you're ending with moles. So again, we're going to apply this roadmap here. Moles of A convert to moles of B. We're solving for oxygen gas, so we need to make sure we put oxygen on the top in the ratio. So it's a 1 mole of oxygen for every 2 moles of hydrogen. So to put this into the calculation part, you take the 0.76 moles of hydrogen gas and you divide it by 2. All right, the moles of hydrogen are going to cancel out, and that leaves you with 0.38 moles of O2. Now, something I have not stated, but I'm applying it, are the significant figures. So you have 0.76, that's 2 sig figs, This is 2 sig figs, so that's good. All right, you always double check your significant figures. This 20.0 is 3 sig figs, so that means that this needs to be 3, which it is. So always pay attention to your significant figures. Okay. All right, so now we're going to go down to a new problem here. And so this problem involves ammonia decomposing into hydrogen and nitrogen gases. So again, we work out the equation, we balance it. Now the question is, if 0.676 moles of nitrogen are produced, how many moles of hydrogen gas are produced? So in this question, we're providing you the moles of nitrogen gas, and then it asks how many moles of hydrogen gas. All right, that's the question. So now we need the ratio between hydrogen and nitrogen gas. All right, so that ratio would give you 3 moles of hydrogen for every 1 mole of nitrogen. So that's the ratio. All right, so writing this out, so you have 0.676, we're going to multiply by 3. Now notice that the moles of nitrogen is going to cancel out here. So those go away, and that leaves you with 2.028 moles of hydrogen. Now, so that calculation is correct. All right, you can check that on your calculator if you want. But I want to make sure the significant figures are correct. So based off of this number here, 0.676, we get 2.03 moles of hydrogen. So that is our answer for that question. All right. Okay, so that was this question. Now, there's a question above that we did not work, and I want you to try to work that on your own here. I'm going to give you roughly 30 seconds, and then we'll go over it, and this will be the last question that we work on. Now keep in mind that as you are working this problem, you want to make sure you understand what they're giving you and what they're asking for you, and then utilize the roadmaps that we've gone over. All right, and so this question says how many moles of nitrogen gas. All right, so and then we're given 2.5 moles of ammonia. All right, so we need nitrogen gas, so we're going to take the 2.50 moles of ammonia, and we're going to multiply that by the ratio because we're going from moles to moles. So it is 1 mole of nitrogen for every 2 moles of ammonia, and that will give you 1.25 moles of nitrogen for your answer. The ammonia goes away. So that's a quick problem there. Okay. Now I want to go ahead and just pull up this last one since it's here, and then that way it's on the board. So this is where you're given grams, and we have not done one yet that pertains to grams. So we're given the grams of hydrogen gas. We're asking how many moles of ammonia are going to react. So remember that grams is, so you're going to take the grams of hydrogen gas, you're going to convert that into moles of hydrogen gas, you're going to divide by the molar mass of hydrogen, and then secondly, so that's the first part, and then the second part will be converting your moles of hydrogen into moles of NH3. And that uses the mole ratio. So there's the work for it. All right, and don't forget to pay attention to the figures. All right, thank you guys for watching, and see you in the next one.